So morning all, we're going to be continuing with magnetism. We're not just continuing, we're going to be finished with magnetism today, hopefully. All right, so that way we can keep on moving. So once we finish magnetism, we're going to go on straight into heat. All right, so heat will take about 4 weeks to complete, and then we're going to have atomic physics. So atomic physics, we're probably going to have to finish next term, or we can knock it out with two-hour class sessions and knock it out to the way. But when we reach that point, we'll cross it, reach that bridge. So let's continue with mutual induction. All right, so that's to revise, just to recap, because it's been a while since I've seen you all, as in this setting, of course. Induction is where we use motion to generate an electricity, right? So that's we should have done this. You all would have done this. If you take a wire and place it in a magnetic field and you move it in a magnetic field, that magnetic field will cause electrons to move out of the wire, thus creating an electric current. All right, so that is what um, that's what induction is. Induction is simply where we have a wire moving in a magnetic field and that creates electricity. Here we're going to look at mutual induction. Mutual induction is a little bit different, but basically the same thing. So let's read from the screen. We have just learned about, we learned about induction before. If we were to apply a current to a solenoid, a magnetic field will be produced. That's what we've been doing. If we place another solenoid within this field, a current will be induced in it, and this is called mutual induction. So let's see what they actually mean by this. Let's get a bit bigger diagram. So I have circuit 1. Seriously? Okay. All right, so I have circuit 1 here, and I have circuit 2 across here. Circuit 1 has a power supply in it, right? It has a battery. So that means it is going to generate, when I close the switch down, electricity is, why does it keep doing that? Electricity is going to flow from the positive pole. Remember, electricity always flows from the positive, right? And the long line is the positive. So it's going to flow through here. And then once current passes through a wire, a magnetic field is generated. And as a result, because of these loops, we're going to have a concentrated magnetic field. So we're going to get a magnetic field being produced through my coil. This is what will happen normally. Let's just say this is what the magnetic field does normally, where we have our south pole and on our north pole being generated in our solenoid. Now, if this first circuit here, this circuit here is sufficiently powerful enough, as the magnetic field in this is sufficiently powerful, that field can extend further out into the space around it. So rather than a small little space, what's going to happen, this field is going to propagate all into the space, into a big area around it. And by placing this second coil, right, if we put this second coil within this field, as in this coil here, and we put it within the field, what's going to happen if I have a magnetic field that just jumped out into space? Wouldn't it be moving? Anybody has a question? Yeah, right. As we put it on, that magnetic field is going to spread out into space and move out, right? The way how magnetism works, when you put a field, it's not like that field is there all the time, right? As soon as you put on this switch, right, the magnetic field is going to rapidly propagate out into the space around it. It does that very, very quickly, nearly at the speed of light, nearly, I tell you, nearly, right? But it still has to move out into the space around. And while it is moving, this magnetic field is going to cause some of the electrons to get bumped out of this wire, because that's what induction is. When you have a moving magnetic field or a moving wire within a field, right? You're going to cause some of these electrons to bump out of the wire and create an electric current. But that only happens for the very second we put this on, because as soon as we put on this switch, right, the magnetic field is going to propagate out into space, not space as in outer space earlier, right, into the space around it, right, and create its proper field. So this is what it does in the first billionth of a second. It propagates out into the space around it. Now, this initial motion of the magnetic field, why are you doing that? Uh-oh, I think my word is going to crash. Anyway, while it crashes, this initial propagation of the field, right, will cause an electric current to start flowing in my circuit. But that only happens with the very second I put it on. Once the field has established itself, it's then just going to exist, out in space as your regular field. And once the magnetic field is just existing there and nothing is moving, so once that field has propagated out into the space around it, right? So it has done this, all right? So this is the field, your magnetic field. It has propagated out. It's now existing there in a static motion. No current is going to flow here again. Why? Because nothing is moving. Remember, for induction to happen, two things have to happen. Either the wire is moving in magnetic field or the magnetic field is moving. Here, my circuit is stationary and my magnetic field is stationary. So as soon as the current goes on here, and as the magnetic field goes on in my first circuit, I will get a very, very quick blip, a really big blip of electric current flowing here, and then it will stop. Why it will stop? Because this has stopped moving. Once the magnetic field has stopped moving or the wires have stopped moving, my current is going to stop. All right, so let's see here. Note, the current will only be produced when the magnetic field lines are cut by the wires of the solenoid. This can be done by, one, moving the coil. So if I had taken the coil and moved the coil back and forth, all right, that is the circuit. That's my coil, 2 here. All right, so if I had taken that and moved it up and down, back and forth within the magnetic field, I would have created an electric current. Or we can move the magnetic field. This is easier to do. And how we can move this magnetic field? We can use an alternating current. What is an alternating current again? An alternating current is one that switches directions many times in a second. And by switching the direction of the current, we are also flipping the magnetic field. Let's just take a look and see what's going to happen here. All right, so this is how they generate constantly moving current or constant current in two coils with mutual induction. So I'm going to have, instead of a power supply here, I'm going to have an alternating supply. So that means at 1 second, my current is going to be moving this way, causing my magnetic field to propagate out into space. And as it propagates out into space, it's going to cause electrons to start moving. All right, so it propagates one direction out into space. Now, the very next fraction of a second, because it's an alternating supply, it reverses its direction. So now what's going to happen? My current is going to flow in the other direction, causing my magnetic field to now reverse. Right? So my magnetic field is now going to be moving in the opposite direction. Right? And when my magnetic field moving in the opposite direction, my electrons are now going to be moving in the opposite direction. So what's going to happen, because I have the magnetic field going forward and back, they have to do the same process over of propagating out into space. And the movement of this magnetic field is what generates our constant current in our coil. So why are we doing this where we have to, it sounds a bit confusing or a bit, complicated. Why are we going to use a magnetic field that constantly reverses itself and creates an alternating current. So let's see. Transformers, not the cartoon, not the movie. We're talking about something that's quite old, much older than both of those. Transformers is one of the most important devices or electrical electrical devices that exist. We would not have electricity in our homes without transformers. We would not have electricity as cheap as it is without transformers. Very, very important, device in modern electricity. So let's read. A transformer is an extremely useful device that utilizes mutual induction. It is used to change the magnitude of a voltage and a current. Now, a transformer. Have you all ever noticed, let me see if I have any here. No. All right. Have you all ever noticed a gray cylindrical box out on an electrical pole? Right? It's a gray cylindrical box. Right? It's on almost every single street will have a transformer on it. Let me see. Let me just pull up a picture for you. All right, so a transformer, just to tell you what a transformer looks like, this is how important. Everybody has seen this on an electrical pole, right?
Yes, miss.
Yeah? All right, so this is a transformer. Transformer, we would not get electricity in our homes without a transformer. This is a regular transformer that you find on every single street or every other street in the country, across the planet. We have transformers. Now, there are bigger transformers out there, but we'll take a look at that just now. So let's look at what the basic design of a transformer is. A transformer consists of a soft iron core. Please note the word soft iron. We'll explain that just now. With two coils attached to it. One coil is your primary coil, and that is attached to the AC supply. I keep forgetting to change this word. All right, so your primary coil is connected to your AC supply, and the other coil, called the secondary coil, is connected to your other devices. Or this is the current that we use once it comes out of a transformer. So first things, let's look at a very, very simple version of a transformer, but this actually works. So we have in the middle here a soft iron core. What is soft iron? Soft iron is basically nearly pure iron. Now, the thing about iron and steel, steel has the ability to retain a magnetic field. All right, so that's how you can take something and pass a magnet over it over and over and over. All right, and it can become magnetized. Pure iron, when you apply an electric current to pure iron, yes, it will generate a magnetic field around it. So as soon as you put on that electric current, it's going to generate a magnetic field around it. But guess what? The instant you turn this off, that magnetic field disappears. Now, if you happen to use steel, depending on the amount of carbon in it, can hold on to some of that magnetic field. So we don't want something that's going to hold on to the magnetic field. We'll see why just now. So we use a soft iron core, which is, soft iron is nearly pure iron, and nearly pure iron is a bit more malleable and it's quite a bit softer than steel. What gives steel its hardness is the presence of carbon. Did you all ever do that in chemistry for alloys? Anybody? No?
Miss,
Yeah.
we just started electrolysis. I guess now we come in effect with like the energetic sample.
Who's your chemistry teacher?
Miss Funky.
Miss who? Pontiflat?
Yeah.
Okay, yeah, I know because she's come and get the wires by me. So I will ask her if she's taught you all about alloys and whatnot. All right, just to recap this a little bit of chemistry because it's going to come into play on Wednesday. Do you all know what the presence of do you know what the presence of impurities does to material?
It makes them work not as well. Yeah.
It can make them work not as well, or it can make them work differently. All right. I know this is completely off topic, but it's kind of something that's going to play into your discussion and source of error and whatnot on Wednesday. Um, the presence of impurities, what does it do to your boiling point of a material?
Lowers the
Lowers it. Wonderful. Right. What does it do to um the melting point of a material?
I'm with you.
About the same thing. It will lower it. All right. Now, as I've said, or you're going to see, especially the topics we're going to be doing, especially atomic physics and heat, chemistry and physics, start to kind of hold hands and dance together. Right. So you're going to get a lot of chemistry-based questions coming up. So here, our first. Oh, there's Tamika. Right. So here we can see the presence of carbon impurity. Now, an impurity is not always a bad thing. An impurity is just something that makes a pure metal not pure, or pure material not pure. All right. So when we introduce iron and carbon, we get steel, and steel holds on to magnetism, right? Because the domains in steel are easy to line up, and they kind of remain lined up after you take away the current. Iron does not hold on to magnetism. So as soon as you take off the current, those domains go back to doing whatever they want. You know, it's like children when you tell them something and the instant we turn our back, or they go back to doing what all they're doing. I'm watching some more in the class. All right. Right. So that's why we have a soft iron core. That does come in the exams. They ask you why we use a soft iron core. Right? Soft iron core because it does not hold on to magnetism when current is not flowing. Very important, as we'll see a little later down. So let's see what we have here. We have our primary coil. Why does it look like a T? Yeah. All right, so we have our primary coil here connected to an alternating supply. Remember, the symbol for an alternating supply is basically a little sine curve. That actually is a sine curve. It's not a squiggly line. It's meant to be part of a sine curve. All right, so that primary coil, this is what we call a coil that's wrapped around your core. Now, all of these wires here are insulated. There is no actual flow of current between the primary and the secondary. No current passes from A to B. What happens here is strictly due to magnetism. So we have our primary coil and then we have our secondary coil. So primary coil, everything here will have a subscript of P, and then we have our secondary coil, and this is where we put our devices, like everything in our house, our fridge, our TV, our computer, our phones, our plugs. This is the load, or the area that uses the electricity. So how does a transformer work? Let's take a look and see. The magnetic flux from the primary coil is transferred to the secondary coil. The AC keeps changing many times a second, which keeps the magnetic field moving, hence ensuring there's an induced current in the secondary coil. It should be important to note that the wires used in the coils are insulated, so there's no actual transfer of current from the primary to the secondary one. So let's take a look at magnetic fields here. This is what the magnetic fields are doing. We're kind of going to think in the back of your head, imagine the back of your head. We still do have that soft iron core here. But again, nothing here is being connected electrically, right? The coils in our, the coils on our primary circuit and our secondary core circuit are wrapped up in plastic. These are insulated wires. Just like how you all know you can hold on to a wire once it's properly insulated and not going to get shocked. So electricity doesn't flow out of the wire. Well, we do know, we've been doing this for a couple of weeks now, anytime current flows through a wire, it generates a magnetic field around it, right? And that applies here. Any wire will have a magnetic field existing around it. But as long as current is flowing, the instant you take off that current, you take off that electricity, that magnetic field ceases to exist. So we imagine this is the soft iron core here in the gray, and we have our primary coil and we have our secondary coil. And what happens, utilizing mutual induction, we can see that the magnetic field generated by our primary coil is going to propagate out into space, right? And it's going to end up passing through our secondary coil. And the instant, because we're using alternating currents, we're going to have our magnetic field moving in one direction, one fraction per second, and then it's going to reverse, all right, and keep on reversing. So this constant motion of going back and forth is going to always, it's going to, not always, it's going to ensure that electrons are always flowing around in my circuit. This circuit here has no electricity connected to it. It is just a coil connected to whatever device you have. It's because of the magnetic field generated in our primary coil that propagates out into the space around it. And once that magnetic field moves through the wire, right, that moving magnetic field is going to bump out some of the electrons, creating our electric current. Well, cool, smart device. If I think, if you think about it, it's like, well, and depending on how many wires we have here, all right, so depending on how many coils we have, we can either increase our current or we can decrease it. Well, I tell you, whoever came up with this, they could actually find out who came up with this. It was brilliant. Simply by changing the number of coils in your transformer, we can either increase our current flow or we can decrease our current flow to our devices that we need to use. So let's see how that's done. Types of transformers. There are essentially two types of transformers. Those that increase, those that increase in applied voltage and those that decrease in applied voltage. So let's look at the names of these transformers, which is kind of honestly real obvious and straightforward names. A step-up transformer, this is used to increase a voltage. Well, duh, if you had a step up, that means you're going to go higher, and higher means to get larger. So step-up transformer, this is used to increase your voltage. And how do we increase our voltage? We use more coils in the secondary, more turns or more coils in the secondary coil than the primary one. And then we have a step-down transformer. This is used to decrease your voltage. And how do we do this? There are more coils in the primary section than in the secondary. Now, the symbol for a transformer, all right, is very, very simple. It's just two lines with, for step-down transformer, you'll have more turns in the primary coil than in the secondary coil. So this will be for a step-down transformer. This is how simple it is. This is the actual symbol. All right, and for step-up transformer, it's reverse. You're just going to have one coil for the primary and a couple coils for the secondary. That's what indicates that you have either something that's getting larger or something that's getting smaller. So how does the amount of coils here make a difference? Why would that make a difference? Okay, now you're going to have to write this down in your own words, but I'm going to explain it to you. So let's get to a basic transformer. Sorry, let's just scroll up. All right, so this is my general transformer, and I want to look at my step-up transformer. A step-up transformer is one that increases the voltage. So suppose I put 5 volts into my primary, all right, I should get a larger voltage in the secondary. How is it going to do that, considering the only thing here flowing is magnetic fields? So how are magnetic fields going to increase my voltage, my current? Let's just assume, right? This is really, really small numbers, right? Let's just assume that every piece of wire here, let's make that brighter. Let's assume that every piece of wire here can generate 100 electrons. We're just imagining. It's actually a much bigger number than that. All right, so that means every single wire here, once a magnetic field passes through this wire, it is going to cause 100 electrons to jump out of the wire and start moving around to form your current. So if one piece of wire, this one loop generates 100 electrons, that means the more wire we use, the more electrons we are going to get forming in our circuit. So here we'll have 400 electrons. So suppose I want to get even more current. All I have to do is put in more wires. Right? And by using more and more wires, I will now have more electrons flow in my circuit. By having more electrons flow in my circuit, I will get a bigger voltage and I will get a bigger current. Y'all, did that make any sense?
Yeah.
All right, real simple. And I was like, hey, that's real simple, right? No set of putting in bigger equipment. All you had to do was, instead of taking your, if this was your coil, all you had to do is take more wires and wrap it around. And by wrapping more wires around your core, that means more magnetic field is going to cause more electrons to jump out and create, right, to go into your circuit or whatever you're using. All right, really cool idea, right? And it works perfectly. So all we have to do to get a step-up transformer, we use more wires. All right, so here the symbol for like number of coils is N. All right, so number of coils in your primary coil is N subscript P, and number of coils in the secondary circuit will be N subscript S. All right, so for a step-up transformer to work, you have NS is more than NP. And there is a very simple relationship and equation that relates them that we're going to come to in a little bit. Now, I want to now look at a step-down transformer. In a step-down transformer, it's just the opposite. So rather than using more coils, we're going to end up using less coils. If we end up using less coils, that means we have less electrons being supplied to my circuit. And if I have less electrons being supplied to my circuit, then obviously, here let's use the example of 100 electrons per wire. Now I'm only going to have 200 electrons coming out from the wire. So that's going to give us a much smaller current being produced because we have less electrons being liberated in my circuit. So for step-down transformer, NP will be greater than NS. You do have a section, I really hope, I did see some of you all printing out your handouts. I commend you, and I'm very pleased when I saw that not last week before, when I saw you all printed handouts. So put it in your handout, write it in your own words, how a step-up transformer works and how a step-down transformer works. Yes, the class is being recorded, so you can look at it again, so you can kind of formulate your own words, because this does come in exams. They ask you, how does a step up and a step down transformer work, or how does changing the amount of wires affect your current in a transformer? So let's go on to the maths. It's the only maths in this whole topic. It's been a long time since we did equations, though. Real long time. Calculations. It's simple, and I kid you not, it's a simple equation, links the AC voltages across the primary coils and the number of turns on each. Really simple equation. Well, it's actually a lot more complicated, but when you work it out, when it works down, it works out a very simple equation. At CAPE, you will do the full equation. But at this level, you just have to know what equation links to what. So let's see what we have on the screen. On this side here, we have our primary coil, and our primary coil supplies the current, and our secondary coil uses the current. So here we have a supply, and here we have a resistor, any kind of device. We use the current in your secondary coil. So let's look at everybody here. We have our primary voltage. Yeah, we have our primary current. We have the number of turns in our primary coil. You don't really need to know EP at this level. That'll come in at CAPE. All right, I use this exact diagram at my CAPE questions. So. And let's look at our secondary. Our secondary, we have our secondary voltage. We have our secondary current. And we have the number of turns in our secondary coil. And the first equation you're going to learn here is the ratio. Just to revise, ratio also means to divide. You all know that. You should know that. All right, so the ratio, we always look at secondary to primary. We want to see how much we get out of your transformer. So if I were to look at my secondary voltage to my primary voltage, so VS over VP is the same ratio of turns. So VS over VP is equal to NS over NP. So my secondary voltage over my primary voltage is equal to my secondary number of turns over my primary number of turns. So if you had to work out anything here, all you had to do is cross multiply and divide. Okay, next day we'll do some questions on this. And then our next equation, which is really, really simple, power, the amount of energy created by the primary coil is transferred to the secondary coil. It does not create more power. It does not create any more energy, right? Because remember, according to the law of conservation of energy, energy cannot be created nor destroyed. It can just be transferred from one place to another. And a transformer is one of the most perfect examples of that. You can't get any more perfect than a transformer. The power made in your primary coil, whatever power you have in your primary coil, and that is because it has power being supplied to it, nearly all of it goes to the secondary coil, nearly all. We'll see how much nearly means. All right, so what we can, because it's nearly the same value, we can take it to be equal. Because if I have, 1 and 0.999, they're basically the same value. At the end of the day, it's nearly the same thing. It's not worth fussing over the little small difference. So here, the power in both coils are the same because they're very, very close to each other. So you're going to have your power, primary power is equal to your secondary power. All right, remember the subscript P indicates primary and the subscript S indicates secondary. And how do we work out power again? Power is equal to IV.
We don't have this on our handout, this power thing.
This is not in your handout?
No. And we reach up the calculations.
Hold on. Let me see. It's been so long, magnetism. No. All the equations probably didn't come true. Okay, the equations didn't come true. That has happened with Word. I wonder if you download it. All right, is there a way to download this? Must be a way. All right, I'll post this back up because the equations didn't come true. Because I'm now looking at it in the Google Classroom. That happens as one of the problems with Google Classroom documents, with Google Documents. Equations, not quite their friend. All right, so I'll post this back up. All right, because this is the original. Suppose. Let's write it down. It's just one line of working. All right, so power is equal to IV or VI, same thing. You all should know that 2 by 3 is the same as 3 by 2, right? So here you can say power is equal to IV or V by I, same exact thing. So you're going to get primary voltage by primary current is equal to secondary voltage by secondary current. Now, if I wanted to do the same thing as I have above here for turns, where I compare the secondary to the primary, let's see what we'll get. Right? I want to get Vs over Vp. So let's just manipulate our equation, see what we get. So to get the Vs on one side, I'm going to have to divide by Is. So let's just say Vs over Is is equal to Vp over Ip. So I'm going to divide by this. I'm going to get Vs is equal to Vp over by Ip over Is. Everybody agree with that? I'm doing step by step.
Yes.
Right. And then I want to carry the Vp across on this side because we want to get this going on. So all you have to do is just divide by that. Let me get some working space. All right, so you divide by the Vp, so you're going to get Vs over Vp is equal to Ip over Is. Now, it's easy to mix up which one goes on top. So what I tend to do, I remember this instead. And then it takes basically 5 seconds to write on the equation, or 10 seconds, and to do the transposing. All right, always find the simplest things to remember, because once your maths foundation is good, you can do any of these proofs once your maths foundation is fine. All right, and then let's just look. If we go back up, we're going to see I had a whole big series of equations. Well, not whole big, it's just a multiply. So this is the other version. If we were to flip it over, we can get Vs over Vp is equal to Ns over Np, which is equal to Ip over Is. Any one of them. So you can use this kind of sequence to work out questions. So we'll finally do calculation questions on the next day. When is the next day I see you all for class? Our next class is actually when we have I won't see you all on Friday because you have biology on Friday. Do you all have biology this Friday?
Yeah.
All right, so that'll have to be an asynchronous class to make up for the missing out day. All right, so we'll do questions on that. So let's go down to the last part, energy losses. The efficiencies of commercial transformers are very high. When I say very high, 95 to 99%. So that means if I were to put in, come on, pen, 10 volts into my primary circuit, my primary coil or whatever, my secondary coil will give me 9.5 to 9.9 volts coming out of it, which is really, really good. As in engines, the engines that we use generally have an efficiency of 25%, meaning we can only use 25% of the energy put into it. But transformers are perfect, near perfect. There's nothing else out there that uses energy so efficiently and wonderfully as a transformer. So that means as much energy as we put in, we get nearly as much coming out, which is awesome because we're not wasting electricity. All right, and you don't want to waste electricity. You don't want to waste energy. That's one of the main goals in engineering and whatnot is to reduce power losses and whatnot. So let's see where we still do lose power in a transformer, because There's still a 5 and a 1% being lost, and we still need to know where we can limit and reduce these power losses. So first one, we have eddy currents. Eddy currents is a real messed up way of losing currents. Let me just indulge your thing here. Let me just get the original diagram. Sorry. All right, so let's go back down. So let's get the original and see what an eddy current is. Eddy currents. Whenever a block of metal moves in a non-uniform magnetic field, or it's in a changing magnetic field, stray EMFs are induced in it. These are called eddy currents, which circulate within the body of the metal. Eddy currents produce heat and other magnetic effects. And to reduce this, we use the coils laminated, meaning it's made up of thin sheets that are separated by an insulating layer of varnish. So let's see what happens here. All right, just look at this. We all know that if I take a piece of metal and I apply a current to it, it's going to generate a magnetic field, right? We know this from the very beginning. Anytime we have a wire with a current passing through it, it generates a magnetic field around it. And anytime I have a wire and that wire has a magnetic field passing through that, or that metal, and that magnetic field is passing through that wire, it is going to create electrons. We know that, right? One is the reverse of the next. So I have here, let's look at this. If I have this primary coil generating a magnetic field, yeah, this magnetic field is passing through or being used, the coils here helping to move it through. It's going to move through and create electricity in the secondary coil. Cool, that is what we want. That is the whole purpose of the transformer. But guess what? This core is also a metal. And this metal, if I take a moving magnetic field and pass it through a metal, this is also going to create a current passing through the core itself. Remember, these things here are insulated, so none of this electricity transfers to the other one. But the mere fact we have a moving magnetic field and this core is metal, using the same concept of induction, a little bit of current is going to start flowing inside of my core. All right, and look at what else happens. I'm going to end up with a metal with a current passing through it. And what happens to metal that has current passing through it? It's now going to generate its own magnetic field. So now the core is going to generate its own magnetic field that is moving opposite to the first magnetic field. You can see how life getting a little complicated here earlier. Right? The core itself now has its own magnetic field. And this magnetic field, as you can see, it's opposite. Right? It's at right angles to the original one. And because we have two magnetic fields interacting with each other, we will end up the first big problem. Anytime we have things interacting negatively with each other, we create heat. And heat is the biggest and the easiest way to lose energy in a system, because rather than all of these electrons and magnetic field flowing nice through space, they're not being interrupted by anything, we now have two magnetic fields operating in two directions. So we are going to kind of confuse the electrons in here. All right, so that's a heck of a thing, right? The whole thing that creates makes your transformer works also is its downfall. The biggest problem in a transformer is eddy currents, and eddy currents is the exact thing that creates your transformer. So how do they prevent this from happening? The way this works, because this is a big block of metal, this big block of metal will generate more electrons. So let's think about, it's a big block of metal, so it has a whole bunch of electrons flowing through it. And the more electrons flowing through it, the bigger the magnetic field, the stronger the magnetic field it will have around it. So that's going to interrupt the other coil even more. But if you use a very thin sheet, right? If you use a really, really, really thin sheet, well, let me use my thinnest pen, right? If I use really, really thin sheets, these thin sheets can only generate a really small amount of current and then therefore a really small magnetic field, right? And when you add up these small magnetic fields, it's still not going to be as large as the big magnetic field that this big block of metal would end up producing. So this is what they do. As I scroll down, what they ended up doing, instead of using the big block, they used to use a big block of metal, right? So it was a big thick block of metal they used to use, right? And then wrap around your wires around that thick block of metal. What it ended up doing, they shaved it down. So they used very, very, very thin slices and they laminated each slice. Laminated meaning let's put a coat of varnish between each slice. So that means they all are insulated from each other, right? And that helped reduce eddy currents to a very, very small amount, which is, again, your transformers are such an amazing device. And the people came up with the way for this to work and how to fix it. It's amazing. Something so simple, right? Still end up having problems, and the solution was kind of ingenious. I don't know who came up with this solution, but it's brilliant. Then going on, let's read the rest. Our second energy loss is hysteresis loss. So hysteresis is magnetism. That's basically what we mean. We talk about the movement of magnetic fields. Each time the magnetization of the core is reversed, some energy is wasted in overcoming internal friction. This produces heat in the core and can be minimized by using alloys in the core. What this means, right? When the current is flowing in one direction, my magnetic field is going to be moving in one direction. When my current reverses, all my domains are now going to line up in the next direction because the magnetic field has changed. Now, by rapidly changing my current, I'm going to be causing all my domains to go left and right or up and down rapidly. Sometimes a few of these domains do not line up the same time as the current, they'll lag behind. And because they lag behind, they end up bumping into the rest. So imagine you have all of these domains all lining up with each other because the magnetic field is causing them to line up, right? And then a few of them sometimes will just happen to not line up in time. Think about it, everybody walking down the corridor and a few people decide to walk up, coming up, up the corridor against you. Obviously, they're going to bounce into people. They're going to slow down the motion of everybody coming out. And this is what we call friction, right? And friction causes heat. As I said, the main heat loss in any single system is always heat. And how they reduce this, they realize that some alloys, right? It's not steel, but they use a different alloy where all of these domains here were easier, or they rapidly change their directions at the same time. So none of them got left behind when your magnetic field kept on switching back and forth. So that happens sometimes. Hysteresis loss is just when your dipoles don't line up in time with each other. Last one here, and second to last one here, we have heating in coils. The heating produced, right, power is given by I squared R or IV, same thing. And how to reduce heating in the coils, because anytime you have electricity passing through a wire, you're going to make that wire heat up no matter what. And how we can reduce this? We just use thicker wires. By using a thicker wire, we reduce the chances of electrons bouncing into each other. That makes sense too. If I were to have the entire school leave through a small corridor, right, where only a few people can walk down that corridor, you're going to have people bouncing into each other. Now, suppose that corridor we had in school was 5 times as wide. Everybody can flow out nice and easy. No one is going to bounce into each other. Well, unless they're not paying attention. That's the next question. All right? And they're going to flow really nice. So how do we reduce heating of wires? We use thicker wires. Simple, simple solution. And the last one here, which is leaves you scratching your head. Flux is your magnetic field, right? Flux here fails to be transferred from the primary to the secondary coil. So for that to happen, you have to be scratching your head, because imagine you had your coils here. This is what your transformer is here. These coils are very, very close together. When I tell you they're really close together, it's not like there's any big separation between them. All right, your primary coil and your secondary coils are so close to each other. It has to be really, really weird. Let me see if I get a picture of an actual transformer for you. All right, so this is what an actual transformer, the inside will look like. That's your actual transformer, folks, there. All right, where we have our, we can see here, we have our primary. This is our primary, and this is our secondary coil. They're right next to each other. So the fact that the magnetic field coming out of this primary coil, Ken, why are you doing that? The fact that the primary field here does not pass through the secondary coil has to be, what? It's like if you are speaking to the person next to you and they don't hear anything that you're saying, and you are speaking normally and your friend has normal hearing. Something weird had to go on, but that does happen. It's very, very rare, but it does happen, where the magnetic field generated at your primary coil, which is right next to it, right, does not reach to the secondary coil. We have no idea why that happened. Well, actually we do, but it's a little bit complicated. So those are all 4 energy losses in a transformer. All right, so you'll read it through. I will repost up this handout with as a PDF, so you'll get the equations that I'm missing. But you all can print it out and write it in. It's like 1, 2, 4 lines, 3 lines of equations. So you can write it in. All right, but I'll still send it back for those who are missing the equations. So
Miss, you know, we got our part. We got this part. The only part we didn't get was some of the equations for power. That was the grand. And you want me for power.
Yeah, that's what I said. The only equations in Google Documents for some reason don't work. All right, so I'm pretty sure if I send you the documents in the WhatsApp group, you all will get the full document proper. So I'll probably post it up in the WhatsApp group, so it'll be easy to get. And I'll still post up a PDF, so that we'll get the full document. All right, so we will wrap it up today there. All right, I know I'm going over class by a couple of minutes, but that's all right. Just to review what we have to do for the next day. All right, for the next day, I want you all, 1, to revise how to convert millimeter cube, not milli, my apologies, guys, centimeters cube to meters cube. 1. 2, how to calculate mass from density. Please, 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 please have that ready, that knowledge in your head, and how to do it come Wednesday, because I am not going to be doing that on the board. We've done it before, and I'm giving you all the heads up. So when we start looking at it in the question, it'll be easy for you all to do. All right, it's just going to be divide and multiply depending on where you are in the question. All right, so that's to tell you all what we're doing Wednesday. We're going to be doing 1, we're going to be calculating the resistance of a carbon resistor. Right, anybody here? Right, so that's one lab we're doing, and the next lab we're going to be working out how much heat it takes to burn a gram of candle, which is a pretty cool little lab. You all are going to be working individually, so you're going to be switching as you go. All right, the resistance lab is very, very short. The candle lab probably takes physically to do about 15 minutes. All right, so we're going to organize ourselves very quickly in the morning. Now, those of you all who have to finish up your magnetism drawing, all right, I have the books separated, so I will just go back and check and see, write down who has to finish up their magnetism drawings. All right, and if you get time, you can finish them up. Also, I did post up the project in the classroom. So those who want to try it can do so. I even put up a little explanation and some notes on it. So it will help everybody to read the explanation and notes. All right. And whoever wants to do the physics project, the deadline is Monday, next week, Monday, to hand up your first draft. Now, if you want to hand it up earlier, all fine by me. Don't ever work just for a deadline because you never know what happens tomorrow. All right. So try to do your work as quickly as possible. All right. And when we come back, so after our labs, I will call those back out for the project just to come in and to finish write it up to do the experiment, which will be one day, not even a whole day. It could be like half a day. All right. And we could get it done. So y'all have a great day and I will see you all on Wednesday. Bye-bye.